Hi guys. Well, we're talking about kinematics, some projectile motion, and today I'm going to go through two examples. If you shoot an arrow straight up with a launch velocity of 52 meters per second, how high did it go? This is the exact same question we're going to be doing when we do our rocket launches, so this math will also apply to that. How long was it in the air? So here's a second question we can ask. Okay, if I'm following my steps, first thing I'm going to do is draw a picture. I have an initial launch velocity of 52 meters per second, and I'm going to say up is my frame of reference, and I'm going to collect some variables. Now I'm going to answer the question, how high did it go first? And so that's going to be up here at this point. That's the H max. Or you could see this as the delta x in the y dimension, or the delta y. There's a couple different ways to annotate this. And so I'm going to collect y dimension variables at the top point. So I have my, so the nature of the projectile motion is that the symmetry of the first half of the launch here and the second half of the launch here. Okay, so if the total amount of time it was in the air was from launch to impact, well, at halfway it would have a top velocity of 0, and that's what we're going to use. So this is what I'm looking for. This is the height. That's the question. The Vy, so the final velocity in the y dimension, is going to be 0 because it's changing direction. It's going from a positive velocity to a negative velocity, and that means that the instantaneous velocity at the top is going to be 0. That's an important implied value. My launch velocity in the y dimension is 52 meters per second. You need to be careful here. We are assuming that I have a 90-degree launch and it is straight up. So there is no initial velocity in the x dimension. All of the initial velocity is in the y dimension. That's another assumption. My acceleration due to Earth's gravitational forces is always down, and so that is opposite of my frame of reference, and so that's going to be a negative 9.8 meters per second squared. And then t half is t up, or half of the total amount of time. Okay, so given my variables here, this is the second question I'll answer, but given the variables here, let's go ahead and try to solve for delta x and the y. So what I see here is that in order to solve for this, I need my initial velocity, which I have, I need my time, which I don't have yet, and then my acceleration, which I do have. Now, you're going to run into this problem a lot in physics, where I'm trying to answer this question, but I have too many missing variables. So what do? Well, I'm going to put this on hold, and I'm going to try to solve for time first. Okay, so I'm going to look at my variables again. I'm going to take a step back. I'm going to say, okay, so maybe not do height first. Let's try and do time first. And so I'm going to do v equals v naught plus a t. I do know my initial velocity in the y, and I do know my final velocity in the y, and so the only thing that I'm missing in this equation here is t. Okay, I'm going to solve symbolically for t. Plug in my numbers. So I'm going to use this 5.3 seconds, which is t half, and I'm going to plug it into here because I want to get to the top. So I should have all my variables now. So I've got 52. So that is my maximum height, assuming I went straight up, straight down. This second question, how long was it in the air? Well, I've already solved for t half, and so I was in the air for t tot, which is t half times 2. So I got 5.3 times 2, which is 10.6. Be my total air time. Okay, so again, we have a picture so that we're understanding it. This is really important for me to visualize which points I'm trying to figure out in my projectile motion. That will guide me as I write my variables. And then when I write, look at my variable list, I'm trying to pick my equations. You might run into a case where you have two missing variables. Put that on pause, try to answer another one of these a different way, and then transfer that over there. And you gotta be careful that your variables all agree with each other, okay? Because I wanted the height at the top, I needed the time at the top. Because I was looking at the height in the y dimension, I wanted the velocity in the y dimension. These are all very important pieces that will become convoluted when we start talking about angular launches. So right now it's all fairly straightforward. Everything's in the up-down of the vertical launch. What we're going to do now is we'll look at the horizontal launch, and we'll look at just the x dimension. I'm hunting from a tree stand, 5 meters off the ground. My bow is still going to shoot an arrow 52 meters per second, so the same velocity. We're just going to change the orientation here. The question is, how far would it go if I shot it straight out? All right, so picture, got my tree stand, and my arrow with an initial velocity of 52 meters per second. The question is, how far? Click my variables. In this case, I'm going to look at the end. X dimension at the end. Now, the nice thing about the x dimension is that all of the velocities are the same in the x dimension. And so Vx, my delta x in the x dimension, and then t at the end. And so I'll fill in what I know. This is going to be 52 meters per second. This is what I need to know, and I don't know what the time is, so we're going to leave that blank. Now, this is an interesting piece that we're leaving blank here. You ask yourself the question, well, if the velocity is 52 meters per second at every point along the trajectory in the x dimension, well, why does a bullet or an arrow or a ball, why does it eventually come to rest? Well, the answer is it runs into the ground. Why does it run into the ground? Well, gravity is pulling it down. As soon as it leaves my bow, that arrow is falling down. And so the amount of time it has to travel in the x dimension at this velocity is the same as the amount of time it takes for the arrow to fall from 5 meters to the ground. And so I'm going to look at the y dimension, and we're going to look at it from the perspective of a fall. So I'm going to look at the top. And so you have quite a few more variables in the y dimension, and the main reason is that the velocities are not the same. So this change in velocity results in some kind of acceleration. I know that it's going to fall for 5 meters, and the initial velocity, because it's a fall, has no initial velocity in the y dimension. That's 0. The acceleration, oh, I didn't set my reference point. The acceleration is going to be in line with my reference point, so it will be positive 9.8 meters per second squared. And these t's are going to match. So in order to get into where I need my answer, I want to solve for t. So I look at my kinematic equations, and I see that where this initial velocity term goes away, and I want to solve for time, and then I'm going to plug in my numbers, and that should be 1.01 seconds. So that's how long that arrow is going to be in the air. And the t in the y is equal to the t in the x, and that's an important concept to understand, that this time variable is our connector. If I'm going to throw a basketball from a free throw line and it has this beautiful arc, right? Basketball hoop, whatever. I'm going to shoot that ball in a beautiful arc. At any given point in time, you could see how far that ball moved in the x and the y. Or at a different time, you would be able to see how far that ball moved in the x and y. So we understand that objects move through space in 2 dimensions, or 3 dimensions rather, with respect to time. right? So a left, right, and an up, down type coordinate system with respect to time. And so that time is going to be a very important connector anytime we have to change dimensions. So I used the information, I had more information in the y dimension, I solved for time, I'm going to be able to use that same time here, and then I can do my x dimension math. Okay, I'm still trying to answer this question. What is the distance in the x dimension that the arrow would fly? And so v equals delta x over time, and I'm going to go ahead and solve symbolically and then plug in what I know. So 52 meters per second for 1.01 seconds would mean it's going to fly 52.5 meters. Okay. So this is an example of a horizontal launch. We'll be doing this in the lab as well. Understand that you need to start in the y dimension and get your time, and then you can take that time to transfer into what happens in the x dimension. And the other thing that we're seeing here is that the x dimension has much less going on in terms of variables and kinematics than the y dimension does. And the reason for that is this guy right here, this acceleration. This acceleration causes a change in velocity, and unless we're talking about a car putting in gas into the engine, my velocity is not going to change. Okay, any hit object, any thrown object, any launched object that has an initial velocity and then no more unbalanced forces after that will have a continuous velocity. Okay, so that is a vertical and horizontal launch example. I hope this helps you with the two labs. When you come to class, we're going to do the vertical launch lab and with the same math that we just did, and then we're going to do a horizontal launch lab, which is this math right here. So, all right, make sure your notes are good, and then I'll see you in class. Good luck. Thanks.